welcome to Engineering Basics Week 10. Today we're going to be doing more intermediate statics. This is part 3 of sort of the second round of statics that we're doing. So today we will be we'll be focusing pretty much the whole day on the method of sections. So this is, again, similar to the method of joints, and we'll go over shortly. So before we get to it, who can tell me what is stress? Ah, this GIF didn't work in the thing. Oh well. Anyone have a good answer for me? I know at least 2 of you do.
What was the question again, Tyler?
What is stress? Same question I start out with every time.
Yeah. You want me to give that, or should I give the other guys a chance?
Go ahead.
They remember. Stress is a force over an area.
Force over an area equals stress. I think.
That's
normally,
also me every night.
That's also what?
That's also me every night.
You're right. All right. What is strain? Someone else? Someone have a good definition for strain?
How much a material deforms compared to its original form.
How much it deforms. So we'll call that U over its original shape. Perfect. So yeah, we've got a thing, and we stretch it, it becomes longer. And we've got a change here. It's U, that's how much it changed over the original length. Perfect. That is delta L over L equals strain. Oh, not 3. Equals strain. There we go. Awesome. Glad everyone's starting to get that set in your head. So today we will be moving on from the methods of joints to the method of sections. So we're going to be kind of drifting away from trusses and more towards frames and machines. So method of joints is really useful when whatever you're making is made up of pinned connections. So even something like a downhill bike, right? Most of these connections can be either thought of as pins or actually are pins. So you've got a pin down here at the wheel, a pin here at the seat. There's 3 dimensions, so it gets a little different up there. But even something like this welded joint here, you can kind of think of it as a pin. However, when we get to more complex structures, that assumption no longer works. So in this downhill bike, right, this big old joint right here, it's pretty hard to call that a pin, right? There's a lot of little stress concentrations. There's a lot of bending moments that will be able to impact however this thing functions in that area. So we need some better way to talk about our whole rigid body, or even our whole machine, where we don't have to take it apart. So enter method of sections. So the idea with the method of sections is that we're going to start off solving the external problem. So we want to figure out what all of our outside conditions are. Then all we need to do is section across the members that we're actually wondering about. You guys will see pretty shortly that this is a much better, well, not much better, but oftentimes a much faster method of doing statics. Especially for problems where you're pretty certain of the information that you're trying to find. So first thing, figure out external equilibrium. Second thing, we're going to section across the desired members, and there's some little caveats there that we'll get into later. But that's fine for now. And then we solve the section as a rigid body. So once we cut it in half, then we assume the whole thing is again a rigid body, with those caveats in mind. We'll get to that. Again, just like the method of sections, we're assuming that everything is made out of members. So we're assuming all of these structures are made out of things that can only take force in 2 directions. it doesn't necessarily have to be two force members, but typically when you're doing method of sections and you start out, you might start out with this method to get an approximation for stuff, and then you'll move on to more complicated methods later, right? So if we have a welded joint here, we'll just draw some mystery elbow, right? We have this welded joint. When we do our cut, we might make a cut here, and then we can start to solve for whatever the reactions are right there. But in reality, you know, this welded joint can probably withstand a significant amount of torsion. So it's not a perfect like physically, if you were someone trying to write a doctorate paper, right? It's not a perfect solution, but this is engineering. It's all about using the resources that we have, making some good, well thought out assumptions to come up with solutions that are fitting for our application. So normally I would start with, well, normally in a class like this, where you would be doing intermediate statics, you'd start with some example like we did last time, some toy example, but that's freaking boring. So we're not going to do that. But I will use this just to show what we're going to do, but we won't run through the example. So step one is do the external statics. So we've got 3 forces here, 4 loads that are being put onto this structure. And then we have 2 places where we can have reactions. So one here, and then one there in the horizontal direction, and not that one. Should be over here. This is the pinned joint. So if I were to just do the quick and dirty FBD of this problem, I'm going to claim that my origin is down at point A. I'm just gonna draw this structure as a big rectangle because it doesn't really matter for the example of the internals. And I've got 1 force, 2 force, red force, blue force, and some reaction forces. I'll draw reactions in blue, because why not? So we've got a slider there and a pin there. So that's our free body diagram. Technically, if I wanted to make Mila happy, I would label X and Y, and then I would label all of my forces here. But we started late, so we're gonna move on. So that's step 1 done. We did our external equilibrium. We'll say, you know, there's 3 unknowns. We have 3 equations. We should be able to solve this. Done, dusted, whatever. Moving on to step 2. So now I want to figure out some problem. So there's some question that I have about this structure. For sake of example, I'm going to say we want to figure out the force, the tension or compression within this member here. I want to figure out how this one is behaving. So to do that, using methods of joints, I would have to start somewhere where I think I have a good amount of information and move on from there. So, you know, it might make sense to start here, because when we're given one force and we can pretty quickly see the other force. Okay, well that one's probably 0 because there's nothing else going on there, because we assume these are 2 force members. Then I might jump down here and say, okay, well if I know this one is 0 because it's not taking any load, then this member here has to take all of the XY, all of the X component reaction from this corner. So, I mean, 2 steps, not that bad. We got to it from method of joints. However, why do 2 free body diagrams when we can do 1 free body diagram? So, what we're going to do for the method of sections is we're literally going to make a section. I'm going to do my section in red. Red seems like an appropriate color for sections. I'm just going to section off the diagram here. I'm going to treat my whole problem as if I now removed this part of it. And whenever I remove something, I have to replace it with something else equivalent. So let's go ahead and jump to a clean page here. So I now have a problem that looks like this. Something like that. So I've still got all the forces that are acting upon this body like this. There was a slider there. But I now have some amount of reaction, stuff that happened over here that I need to figure out what to do with. And I can use the fact that these are all 2 force members to place my unknown reactions. So I can say, well, I know this member has to have some reaction here, or there has to be some force going into this member in this direction. Is right there. This is a 2 force. Oh, we're assuming that this structure is made up of 2 force members. So this member can only resist something in that direction. I know this member can only resist something in that direction. And I know this member can only resist something in that direction. So at first you might be thinking, well, how is this any better? Now we just have, now we have some other problem that has 3 unknowns. However, because that we're doing methods of sections and not methods of joints, we have a 2-dimensional problem. So that means we can use sum of moments. Or sorry, not x, that should be a point. We'll say the sum of moments about a equals 0. So we're no longer dealing with the particles. So instead of just the 2 equations, just f of y equals 0 and f of x equals 0, we now have a third one. So we have three equations we can use, 3 unknown forces. Because remember, we solved that one in the first step. This was our reaction at that slider. So now rather than doing 2 separate free body diagrams that we had to do with joints, we just do one and we solve one statics problem. For this toy example, I would argue that the method of joints is actually probably easier, right? Because you have 2 really, really simple statics problems. However, a lot of times it's hard to see that, or it can be difficult to kind of figure out, well, what joint should I start with? And you end up doing a lot more writing than you need to anyway. So moving on from here, and again, I don't want to spend too much time on this one. We'll get on to the fun one. We can see, okay, I'll call this A, call this B, call this C. And if I'm smart about how I do this, well, I can already from observation tell that B, C, and A are the only forces that have any component in the x direction, right? So if I were to write out my f of x equation, I would get something in terms of variables. So plus something in B, right? Something in A plus something in B plus something C times C equals 0. And for all intents and purposes, right, this equation isn't very useful to us. We could do all 3, and we'd have 3 unknowns. We could do it, we do the math, or we can think a little harder, think like some engineers, and say, well, of my unknown forces, B is the only one that has a component that acts in the y direction, and all of my other y component forces are known. So all that I actually need to do for this problem, because I'm doing the method of statics, I can just say, well, the sum of the forces in the y direction equals 0. I have this known, so we've got one known minus another known. We'll call this known 1, known 2, minus known 3. You know, this is why they always say to label your forces, because then you just get stupid variable names like this. But that's besides the point, right? We've got one unknown, one known force, one known force, one known force, right? These are all just numbers. They're just, could be 50, 25, 10. I don't remember exactly what it was in the problem. And then all we have to add from there, we say plus B, what would that be? Sine theta. If I call this theta, then that would be, sine. So B times sine of theta equals 0. And now I have one equation with one unknown. So I only have to plug one thing into my calculator, and I'm done with this problem. So sweet. Now we have some method where, even though we could have done it with the method of sections, this method in a lot of cases ends up being much faster. It's much easier for us to go about it. And one thing that we'll find out here shortly, too, is that you can use this method for weirdly shaped members. We can use this method for members that either might not be two-force members, and we can use it for more complicated things that aren't just joined at joints, joined at pins. One thing to keep in mind when you are making your cut. So, right, I kind of arbitrarily decided I wanted to make my cut here. For this problem, right, the whole goal of doing this statics problem was to figure out the internal force in this member here. So, obviously, we want our section cut to go through that member, right? If I did a section cut over here, well, sure, then I could solve for this member, and this member, but that doesn't really do me any good. It doesn't make the process any faster, right? It's not wrong, per se, but the whole point of doing the method of sections here is to make it easier for us, to make things faster. The second thing you'll notice is that I cut all the way through the body. So I didn't just make some cut through this member here. In order for the method of sections to work, you have to cut straight through the body. You have to enter it on one side and leave it on the other side. If you just cut a body in one place, like if we were to just cut it here, well, then we have some problem that looks like this. So we've got something that looks like that, and some force just floating around in the middle here. And, well, this is now an internal force. So we run into the same problem that we had before we even started talking about these advanced methods, where we're solving for an internal force with external constraints. So we can't just cut through our one member that we want. We have to cut all the way through the body so that we essentially free it from whatever happens on this side. And remember, we're freeing it from one half of our cut, and we're replacing it with equivalent forces that behave the same way. So the last big thing to watch out for when you're doing the method of sections is you only have 3 equations to play with. So in theory, you can make your cut whatever shape you want. So I could actually make my cut look like this, right? And I could do that to do method of sections for either this beam here or that beam there. Right? I enter the body and then I leave the body. So I'm never stuck inside. I'm never having to figure out internal forces. I turn what were internal forces into external forces. I always have to cut entering it in one place and exiting in the other place. But it doesn't have to be a straight line. So I can make a cut like that. I can make a cut shaped like this, right? I could go all the way over here and come back and then cut there, right? It doesn't actually matter what shape this cut is, as long as everywhere that I cut my system, everywhere that I cut into the truss or the machine that I'm dealing with, I am able to replace it with some reaction, some force. There's some force that I can put there that is equivalent to had I not cut it in the first place. Now, one tempting thing to do when you're doing problems like this is to go, well, I'm just going to make a cut 1, 2, 3, 4, 5. Now I can figure out what's going on for all 5 of these members all at once. And well, the issue with that is we only have 3 equations. So if we cut through 5 members, well, we have 3 equations now and 5 unknowns. And by the rules of middle school, or I guess high school algebra, right, you have to have at least as many equations as you have unknowns in order to solve your problem. Now, because because we are replacing these with equivalent reactions, right? This is a legal move, right? There's nothing there's nothing fundamentally wrong with this problem. It's just then that it kind of defeats the purpose of doing a method of doing a cut that is of doing the method of sections, right? Because now what we'll end up with is 3 equations with 5 unknowns, and we'll have to do another cut or a method of joints, or we'll have to find some other way to give ourselves more equations with which to solve those variables. So typically when you're doing method of sections, you want to only cut through at most 3 members at a time. For most purposes, well, I shouldn't say most purposes. Often, if you're doing a problem like this, there are convenient places to make your cut. And remember, we can make the cut whatever shape we want. So if I care about, let's say I cared about this member here. Well, I could make my cut like that, right? So it's still entering the body and leaving through the outside of the body, right? I'm not just cutting it in one place. But we now have 3 unknowns here that are useful to us because we can use 3 equations to solve that, and we don't have this situation where we have some extra equations to deal with. So before we move on, are there any questions? I know I ran through that fairly quickly. No questions? I mean, I'm flattered, but I assumed something was confusing.
Nah, just a lot of review for me.
Cool. Awesome. All right. Then we'll move on to the fun stuff. Let's do a real problem. So this is the Baja Chassis. I have some issue with the rules. I think that this tube right here, I think that the thickness or the diameter of that tube is too big, right? You know, rules tells us that it has to be at least 1.25 inches. Oop, not 1.25. 1.25 has to be at least 1.25 inches in diameter. And I don't remember what the thickness is required by rules, but I know our chassis is 0.65 for these overhead members. And let's say I'm the new chassis lead, and I think, well, we can lose a bunch of weight if we just shrink those members. What's the worst case scenario I could think of that these members might experience? And the problem that we're about to do is definitely not the worst case. However, it's a good case to consider. And this is definitely something that a chassis lead would need to consider in order to design our chassis. So I know, because I asked the composites people, that the front skid plate is designed to take a 10G impact load. So for those of you that aren't familiar with that notation, this just means whatever force hits this is equivalent to accelerating my body at 10 times the acceleration of gravity. So the Baja car plus driver, we can comfortably say is about 500 pounds. So that's approximately, we'll call this our knowns, right? Our knowns. We know that the mass of this vehicle plus driver is about 500 pounds. So because we're using convenient English units, convenient imperial units, a force of 500 pounds is the same thing as that same mass, 500 pounds mass, being accelerated by 1 times the speed of gravity, or 1 times the acceleration of gravity. So that means if it's a 500 pounds mass vehicle being accelerated 10 times the speed of gravity, then this force is equivalent to 5,000 pounds. 5,000 pounds. We've got our the easiest way to think about this is if I were to throw a block down into the ground, if I were to just drop it, it would accelerate as its own mass. If I were to throw it down, you might think of it as if now it's twice as heavy, and when it impacts, it's going to have twice as much force because I forced it down. But that's one way to think about this notation. So the front skid plate here is designed to take an impact load of 5,000 pounds, and I think, you know what, that's a good place to evaluate my chassis at, right? If the chassis can withstand 5,000 pounds, then that means the skid plate will break before the chassis breaks, and the driver should be safe because we've already accounted for some safety factor in here where this is already stronger than this is already potentially stronger. This is our designed failure mode for a front impact than the rest of our system. So I know that now I have a 5,000 pound load from the front. Let's go ahead and slap some dimensions on here. This is going to be real rough because I forgot to look these dimensions up, but I believe the sims are at about 18 inches from the floor up there. That might be more like 2 feet. Whatever. We're going to call it 18 inches for this problem. And let's assume that we run into some concrete wall right on the front hitch there. So we'll assume that this is a 5,000 pound force right on that tow hitch. We've got the mass, our center of mass. We can say we'll say that the driver sits here-ish. I guess the driver's taller than that. The driver sits there-ish. The engine's kind of like that. That probably means our center of mass is somewhere around here, right? About probably somewhere in the middle, maybe forward a little bit, right? We don't want weird suspension issues. So probably right about there. We'll call it 3 inches below the sims. And this will say that from the center of the firewall, let's see, if I had to approximate, what would that be, about a foot? Sure, we'll call this a foot. These are super rough dimensions, so please never ever take these at face value. There's a good chance that they're wildly inaccurate. However, they're good enough for this demonstration. So I'm gonna go ahead and move. We're gonna move the center of gravity. I'm gonna move that down to there, and you know what? This body can. Oh. Ooh. Spoiler alert. We'll just go ahead and erase that. We don't need you anymore. Okay. So let's go ahead and draw what our problem looks like. So I've got a chassis, looks approximately like that. Something on the front, curves around. Got a firewall, side impact member there. Got a center of gravity, center of mass, right? We have a 500 pound force that acts from the center of mass. We've got a 5,000 pound impact force. And then we've got some reactions at all the suspension joints. I'm going to, for the sake of simplicity, say that let me get some dimensions on here in a sec. But for simplicity, I'm going to say that our wheels are attached by one single point, and they're both in convenient locations. So we'll just say that we have one wheel that will have a reaction here, one wheel that has a reaction here. And because we want this to be a statics problem, right, we need to say that the driver's applying the brakes. So they were most likely accelerating into this wall. The wall hit them, and now they've instead of this being a dynamics problem where we would have some rapid deceleration, we'll just say that they applied the brakes right as they hit the wall. So the sum of our accelerations is still 0. So we've got a braking force here. This will be we'll call this the front wheel. So wheel front, and we'll call this wheel rear. And we'll put my dimensions back on here. This is 18 inches. This is 2 inches. We'll call this one, how about 8 inches? Call that 8 inches. And then let's see. So the whole car is about 7 feet long. So that means from here to there, call that 1 foot. Here to there, we'll call that another foot. And then we'll say this is 2 feet away, and this is another foot from there. So that's 1, 2, 3, 4, 5, 6, 7. Sure, that sounds about right. Now we have a decently well-defined problem of that has all of our external conditions, and this is essentially what we needed to do to set up step 1. So I've got X and Y, and now I have a free body diagram that has all of my external forces, and I could, if I so wanted, solve for each of these reactions. So we'll go ahead and do that really quickly, assuming we still have time. Oh yeah, we still have time. So let's start with the sum of the forces. Sum of the forces in the x direction equals 0. So we've got a 5,000 pound force in the negative x direction, and then plus BF plus the braking force equals 0. So we know our brakes are applying a force of 5,000 pounds. Easy peasy. 5,000 pounds. Now we can do the sum of the forces in the y direction. So I have a 500 pound weight force. So 500 pounds going down, plus the force from the rear wheel. So wheel rear plus wheel front equals 0. So there's another one. And lastly, we can do sum of the moments. So the sum of the moments, I'm going to say about the center of gravity. Actually, I'm going to say about a point right above the center of gravity equals 0. So the sum of the moments about, why not? We can, yeah, no, I want to do it about this point. So the sum of the moments about point, let me give this a name. We'll call this point F. Not F, that's not a good name for a point. Point P is a good point name. So the sum of the moments about point P equals 0. So because of my conveniently chosen location of point P, this should make it a little bit easier to figure out where everything's coming from. So the braking force, right? We said that everything from the wheels is being applied at the shock. So I can slide this vector up to the shock. Oh, and I guess I only get the vector, not the label. There we go. So because I, in this example, removed the wheels, and I'm just concentrating here, I can say that, okay, this braking force is applied just at the location where the shock's attached to the chassis. Because, right, our whole idea here is to figure out what is the reaction, what is the load going through this member, this diagonal, it is diagonal and attached to the overhead member of the chassis during a 10G impact load, assuming everything's rigid. So we've got, from this point, we've got one force here with some moment arm. So we've got WR, I'm going to give myself a little more room here, WR times 1 foot, 2 feet, so times 24 inches, times 24. plus another force here that's acting again 2 feet, so at 24 inches, plus 24 times the front wheel force, plus the braking force is a horizontal distance from our point of 8 inches. So if we were to slide that vector along our line of action, that tells us how big the moment is. So that's 8 inches, so plus 8 times braking force equals 0. And I know some of you that are less familiar with this might be wondering, well, why didn't we have to worry about gravity or about this 5,000 pound force? And that's one of the reasons that I chose point P, is that I can automatically eliminate even thinking about either of these. So because I chose the point where these two intersect, where the line of action of these two forces intersects, the distance to that point is 0. So therefore the moment acting on that point is also 0. And I could just easily have chosen this point. We'll call it point A, right? I could have just as easily chosen point A as the place that I wanted to sum the moments around, and that would mean that the front wheel force and the rear wheel force canceled. And that probably actually would have been a better decision, because that means that now I have one equation with one unknown. Then I basically get that equation for free, which makes this one easy to solve. But I happen to choose this one. Maybe I have some other problem that I need some other things for. Whatever. This is the decision we made. So now we can plug all this stuff in, and let's go ahead and go through the math here. So BF equals 5,000 pounds. So this will be WR equals 500 minus WF. And then we can replace it here. So we have 500 minus WF. That's the force in the front, times 24, plus 24 times WF, plus 8 times 5,000 equals 0. And does someone with a calculator out have that solved already? If not, I'm going to plug it in. Interesting. So we've run into a conundrum here. So because I chose to solve for WR here, right? If I expand this out, then I end up with, let's see, 24 times 500, or sorry, times 5, not 5,000, 500 is 12,000 pounds. I end up with 12,000 minus 24 times that force plus 24 times that force equals 8 times 5,000 equals 40,000. Say 40,000. And these end up canceling out. So that means I did something wrong along the way, right? Because I'm now left with some useless equation. So let's figure out what I did wrong. Where did I go wrong?
Shouldn't one of your wheel forces be negative because it'd be going the opposite direction around P?
Yes. Ah, there we go. There's our answer. Perfect. All right. So yeah, we have, when I did my moments, I was not careful about the directions that I put these moments in. So let's look at WR here. So I assume, and it's usually customary to assume, that positive moments are moments that go counterclockwise, right? When you're in algebra, you learn that angle increases as you lift off of the x-axis. So in engineering, we assume the same thing. And that's, if you've ever heard of the right-hand rule, that's the idea here. So you put your right hand with your thumb right on the origin, and then the direction your fingers curl in is a positive moment. So this force here, WF, is going to rotate about point P in the counterclockwise direction. So that should be a positive force. However, this moment here, WR, is going to rotate about point P clockwise. So that's going to actually be a negative moment. So yeah, thanks for catching that. So this means that this should actually be a negative value here. So this means that rather than being 500 minus WF, this will now be minus 500 minus WF. And need some more room for math here. Let's see, this was minus 500 minus WF times 24 plus 24 WF plus 8 times 5,000 equals 0. There we go. So now we should have WF times 24 minus 12K plus 24 WF plus, let's see, that's 40K equals 0. And now I can say 48 WF equals 40 minus 12 is 28. Yeah, 28K would be minus 28K. So WF equals minus 28 over 48. So whatever that number is. 28 over 48 is 583. So the force at wheel F is minus 583 pounds. So if I go back to my diagram here, this means that the force at this wheel, the force that the suspension's providing here, is it's actually pulling on the chassis. And in this scenario, that's probably a weird thing to think about. But the idea there is, you can think of it as the suspension acting as a spring, trying to rebound the chassis back towards it. So if in some circumstances I would redraw this force in the other direction to make everything positive, for now, I'm going to say it's fine. So we've got that the force of the front wheel is minus 583 pounds, which means the force at the rear wheel is going to be 83 pounds, right? Because minus 500 plus, other way around, 1,083. So back to our next page. So this means that minus 500 plus force at the rear wheel plus, or I guess minus 583 equals 0. You all know how to do math. Rear wheel force equals 1,083 pounds. So we think about that, right? If we're hitting a wall head on, and we're assuming that our brakes are equally stopping us in that direction, well, it makes sense that we'd have to be pushing down on this car. We'd have to be pushing it, like driving it into the ground, into those rear wheels. And you know, this scenario is probably not the best to model using methods of using directly statics methods, but you know, for sake of argument, it's worth it to go ahead and go through the exercise. This could be something like if we were doing collision tests and we had the chassis on a sled, right? Well, then it might make sense, right? If we have some big sled under here, so we make sure that our collisions always end up being predictable, and we just pinned the chassis at those 2 points, then that's more reflective of what would probably actually be going on here. So this is probably better served by assuming this is a collision test. But anyway, now we finally are done with step 1. So step 1, whenever you're doing methods of statics, often step one, or whenever you're doing the method of sections, step one is usually the hardest. And the thing to keep in mind with both the method of joints and the methods of statics is that at the end of the day, we will have to do 2 statics problems. So we always have to do external equilibrium. We always have to do external equilibrium first, and then we can start taking apart our frame or our machine or our truss in order to figure out the internal forces. So hopefully we've mitigated that by now, and now that we know the forces being applied at these 3 locations, now we can start to figure out, okay, what's going on in this member here. So remember at the beginning, that was the whole idea. The whole question is, how does this member look? And I'm sure you guys can see where I was going, or if you saw the spoilers, we're going to make a cut right along those members. So the method of sections and the method of joints, for that matter, do work in 3 dimensions. We're going to leave it as a 2D simplification, but in 3 dimensions, the process would be the same. So in this case, we'd have one reaction here, one on the other side, and then in the back of the car, we'd have to do one for each point on the suspension, or if we were feeling lucky, we could consider these all 1 point and just do one big location for our forces there. But we could still solve the external equilibrium, right? We have one big force that acts, one 5,000-pound force that acts here. We solve our external equilibrium, and then we can start to take this, we can cut this section. We assume the chassis is rigid now. We can cut it straight through. So in 3 dimensions, we have 6 equations and 6 unknowns. We'll leave that to either further research, or if someone wants to go watch, I believe it was episode 5. I think it was the 5th week where we did 3D equilibrium. But in 3 dimensions, you have 6 force equations. So if we do it this way, well, we've got 1, 2, 3, 4, and then I cut this right on the firewall, right at that joint. So that would be 5, 6. So this would be one example where I would then only have to do one more problem to figure out all 6 reactions. It's in 3 dimensions, so it's going to be an ugly problem. It's going to be a lot of little trig stuff going on, but it's doable, and I only had to draw a free body diagram twice. But we'll leave ourselves in 2 dimensions. We'll make a 2D simplification, right? The chassis, other than the one diagonal bar in the firewall, the chassis is pretty much, and I guess there's a little thing back here, but other than that, it's pretty much symmetrical. I think it's a fair assumption to say that it's going to be even on both sides. So that'll simplify this to a 2D problem for us. So now we can take what we did before. We'll make our cut here. Make our cut right through there. We go back to this, right? We're going to make our cut just like that. Right through there. And we've cut through 1, 2, 3 members here. And you know what? We can simplify it. We'll say we cut through that member instead, just to avoid this big question mark. And now we can continue on with our problem. And I actually like that better. So we're going to assume that we cut there instead. So for all intents and purposes, this will act in that direction. So now we can do this problem again with we can go on to step 2 or 3. Which one did I call it? It would be step 3 here. We solve the section free body diagram as if it were a rigid body. So on here we go. Now I need to redraw this as my free body diagram. So we've got 5,000 pounds here. I said I made an assumption that these simplify to one joint there, and that's going to be EF, which was also 5,000 pounds. 5,000 pounds. And then we've got the front wheel, which was 583, right? Yeah, minus 583. So then this is going to be 583 going down. And our center of gravity still acts on this model as a point located right there. This is CG, which is 500 pounds. Often when you're doing problems like this, it'll start to get problematic if you're doing methods of sections and using your center of gravity. Because if you think about it, right, if we cut half of this body off, well, now we're, what do you consider as the center of gravity for this new rigid body? How do we know that the center of gravity was inside our cut versus outside our cut? For the assumption that I'm making, I'm going to say that it was inside our cut, but that's not necessarily good practice. I think in reality, we would probably not even consider the weight force of the chassis. Right, this would be a negligible force as far as our whole system is concerned. So usually we don't really consider that, but I'm going to leave it in for now, and we'll go from there. Right, this whole thing is an exercise. Part of the idea here is also to see what some good and bad assumptions are. So because I'm assuming these are two force members, that means that I now have to have one reaction here, one reaction there, and another reaction going that way. So in order to be a good free body diagram, we need some what are these called? Coordinate system. I'm going to this time draw my coordinates about this point. So we'll call this what I previously called point P. So remember, this was 2 inches away, and this one was 8 inches away. Is that what we said earlier? Yeah, 2 inches, 8 inches. 2 inches, 8 inches. And then these forces are 2 feet apart. This dimension here, 18 inches. And there we go. So now we have a free body we almost have a free body diagram. We need labels, X and Y. There we go. Completed step 1 of, well, part 1 of step 3. Have a free body diagram. Now we just do our sums of forces and moments. So sum of the forces in the X direction equals 0. Sum of the forces in the Y direction equals 0. And sum of the moments about, I like point P. I think it makes sense to stick with point P. Still equals 0. One tidbit of information that's probably good to know. The chassis tube here is offset by 30 degrees from horizontal. 30 degrees? Yeah. Yep, that'd be 30 degrees from horizontal. Or from vertical, sorry. Then I suppose we also need to know, where does that tube, where's the location of this force here? So when we're going to do our, when we're going to start to do our moment equations, we'll need to know that angle. And I guess for our force equations too. So let's see. If we assumed that was 2 feet, this is probably 2.5 feet. So 24th, we'll call this 30 inches. So from U to U is about 30 inches. Okay. Now we can go from somewhere. We have something we can work with. Okay. So, on the next page, I'm sure some of you are already starting to get familiar with what we're doing. So, let's start out. What do you guys want to start with? We can either do sum of the forces in X, sum in Y, or the sum of the moments about point P. What do you gentlemen and ladies? I didn't check the Discord. What do you guys prefer?
Just as like a personal preference.
Well, it is personal preference, right? There's no wrong answer, but there are answers that are potentially better, right? So there's a chance that we might not need one of these. I don't know if that's true for this problem, but is there anything that maybe stands out?
Well, the member we're looking at is the only one that goes in the Y direction out of the blue ones.
Right. Good point. So yeah, the member we're looking at, member that we're talking about here, is the only one that we cut through that goes in the Y direction. That means even though we could use the sum of the forces in X or the sum of the moments about point P, we don't actually need to because we were clever with where we put our cut. So we only now have to do one equation. All right, so let's do that equation. So the forces in Y, we've got a minus 500 minus 583 plus, this is going to be the cosine of 30. Cosine of 30 times our force. Oh, and I made the mistake again of not labeling my forces. I should do that. We'll call this one A, P, and C. Oh, I guess I should call this something else because I labeled that point A earlier. So we'll call this one force B. Why not? B. So this is B now. So plus cosine B equals 0. And this should be a pretty darn easy problem, right? Cosine of 30 is root 3 over 2. So we've got 500 plus that times 100 divided by root 3 times 2, 644. So although we had to do a lot of work at the beginning, right? Now that we have the method of sections, we only had one equation that we actually needed to worry about to figure out the tension going through this member. So I ended up with 644.7 pounds going through that member. And just thinking about it, right? If you had a steel bar for some 4130, you could conceivably see putting 700 pounds of pressure on it, right? If you had this is the largest of any of the tubes on our car, so it makes sense that it could see about a 700-pound load. But we can actually check that, right? We have the tools from what we've done before, from our definition of strain, to actually figure out if this is going to be strong enough. So we've got a tube here. This is 4130 alloy steel. We're going to go ahead and assume that it is annealed. And if I wrote my numbers correctly, this has a yield strength, sigma yield, of about 66,000 psi. And it has an ultimate strength of about 81,000 psi. So, who can tell me what our definition of stress is? You guys did it earlier. Should be real easy. Stress equals force over what?
area, sorry.
Perfect. Force over area. Okay, so we now know we have an axial force. So we know the force is 644.7 pounds over some cross-sectional area. Well, we know the outer diameter of this tube is 1.25 inches. We know the thickness of this tube is 0.065. So let's see. We do 1.125 squared over 4 times pi. That's the outer circle minus the inner circle, which would be 1.25 minus 0.0625 times 2 squared over 4 times pi equals, and let's see if someone beats me to it, 1.25 squared minus 2.06, oh sorry, that should be 0.065, not 0.0625. 0.065 2 squared that times pi over 4 should be a cross-sectional area of 0.242 inches squared. So we'll plug that into here, 0.242, and that gives us a stress of U divided by U, 2.66 K. So 2.66 KSI, or 2.66 thousand PSI, which, lo and behold, is well below our yield strength. So, cool. Our chassis is not gonna be the thing, or at least that that member of our chassis should be strong enough for a 10G horizontal impact. Some of you might be saying, well, shit, if it's 66,000 minus 2.6 thousand, that's a safety factor of almost 30, right? Why would they have to be so big? Why do they have to be so thick? The real issue with those members is actually the bending strength. So with some, I believe, a rollover, the bending in those members is decently high. And actually, in reality, the reason that we use 1.25 inch 0.65 is because that's what it says in the rules that we have to do for the overhead members. But there are plenty of our chassis members that we do actually downsize from the rules, which you're allowed to do if you can prove that they're strong enough to do so. So we go back to where we started, back to the front of this problem. We now know we can make a conclusion that this member here, that would be the overhead member, is strong enough. Woohoo! One thing that I didn't do when I decided this was a 2D problem, I essentially said that half of each side is taking up the force. So in reality, right, our cross-sectional area here isn't just going to be the thickness of one tube. It's going to be the area of both tubes. So actually, I should divide this by 2. So really, the stress that we're seeing in this load case with these assumptions is only about 1.33 KSI. So sweet, our chassis is super strong. That is an awesome answer to our question of, is someone going to die in a front impact? So I feel like we've probably gone, oh boy, yeah, way over time. So I'll wrap this up quickly. So today we went through very rapidly method of sections. You know, we briefly talked about the center of mass, but we'll get more into depth, more into that next time. But we were also, while doing the method sections, we were able to practice some of the methods, some of the mechanics and materials that we actually learned previously.